Hello everybody, welcome back to my channel. Today let us discuss one of the important organic synthetic reagent DDQ, otherwise called 2,3-dichloro 2,3-dichloro 5,6-dicyano 1,4-benzoquinone 2,3-dichloro 5,6-dicyano 1,4-benzoquinone. You know, this reagent has very important applications such as in aromatization of cyclic alkenes, extension of conjugation, oxidation of allylic and benzylic alcohol, formation of alpha beta unsaturated ketone, and intramolecular cyclization reaction. These are some of the important applications of DDQ. In this video, we will discuss all of these applications one by one with important examples. Okay. One of the important application of DDQ is aromatization reaction. It aromatizes the cyclic alkene to corresponding aromatic compounds. In this reaction, DDQ dehydrogenate the cyclic alkene to corresponding aromatic compound. In this process, for example, cyclohexene to benzene transformation or conversion, DDQ first absorb a hydride ion from allylic position of this cyclohexene, to form an allylic carbocation. You know, allylic carbocation is somewhat stable because of the resonance or conjugation with this double bond. Here, a positive charge is formed by the absorption of hydride ion from this allylic CH2 group by the DDQ. That is the first step. Thereby, allylic carbocation is formed. Then, from this allylic carbocation, a hydrogen is then captured by the DDQ molecule. Oxygen of carbonyl group of DDQ molecule to form a double bond here. Here, this hydrogen atom is captured by DDQ as proton. Thereby, a double bond is formed here. Then you can see here is an allylic position, and this allylic position, from this allylic position, DDQ again captured one of the hydrogen atom as hydride ion to form another allylic carbocation. And again, this allylic carbocation remove a proton from the alpha position, and this proton is captured by the DDQ molecule. Thereby, a new double bond is formed here again, forming the benzene molecule. Okay. The mechanism is shown here. Here you can see it is cyclohexene. It is DDQ. DDQ first capture a hydrogen from cyclohexene as hydride ion, and thereby the bond shift from here to here, and this bond shifted to here, and this bond to here. So we will get this anion. Okay, along with the allylic carbocation. It is the allylic carbocation. Okay, now this anion capture the hydrogen from the alpha position of allylic carbocation as proton. Thereby we will get cyclohexadiene. Then this cyclohexadiene having allylic position here or here, CH2, both the CH2 are allylic CH2 group, and we can say one of the hydrogen, as in the previous case, is captured by another molecule of DDQ as hydride ion, forming an allylic carbocation, a new allylic carbocation, along with this anion. This anion again capture hydrogen from the alpha position of allylic carbocation as proton to form benzene. Here benzene is formed along with this para dihydroxy benzene derivative, okay, as the byproduct. It is the mechanism of formation of benzene from cyclohexene or aromatization reaction. It is an example of aromatization reaction given by DDQ, or by using DDQ we can convert cyclohexene to benzene. Aromatization takes place during the process. This is one of the important applications of DDQ, right? Another example of aromatization reaction is conversion of tetrahydronaphthalene, 1, 2, 3, 4 tetrahydronaphthalene to naphthalene by DDQ. Here also the mechanism is same as the previous mechanism. That is, DDQ first capture a hydrogen atom as hydride ion to form a benzylic carbocation. Here a benzylic carbocation is formed. Benzylic carbocation. It is more stable carbocation. And in the next step, a hydrogen atom is captured by this anion, which is obtained as the byproduct in the first step, as proton to form a carbon-carbon double bond here. A carbon-carbon double bond here. So you will get this product. Again, this product reacts with DDQ, or DDQ capture a hydrogen atom from allylic position of this molecule as hydride ion to form an allylic carbocation. Here an allylic carbocation is formed. This allylic carbocation eliminates a hydrogen from the alpha position as proton, which is captured by the anion formed during the reaction to form naphthalene. Here naphthalene is formed. A new carbon-carbon double bond or a pi bond is formed here, so that we will get this naphthalene. This is also another example of aromatization reaction given by DDQ, right? See this example. In this example, 1,1-dimethyl 1, 2, 3, 4 tetrahydronaphthalene gets converted into 1,2-dimethyl naphthalene. 1,2-dimethyl naphthalene. Here aromatization takes place along with the rearrangement of methyl group. Methyl group here shift from one of the methyl group here shift from this position, first position to second position, and so we will get 1,2-dimethyl naphthalene. Aromatization along with 1,2-methyl shift, 1,2-methyl shift, right? The mechanism of this reaction can be represented like this. First, DDQ capture a proton from this benzylic, capture a hydrogen as hydride ion from this benzylic position to form benzylic carbocation. Benzylic carbocation. It is more stable carbocation. And this benzylic carbocation eliminates a proton in presence of the anion formed here to form a carbon-carbon double bond. Here a carbon-carbon double bond. A new pi bond is formed between these two carbon atoms. And as this molecule is formed. Again, this molecule reacts with the DDQ. DDQ capture a hydrogen atom as hydride ion in this allylic position. It is the allylic CH2 group, allylic position as hydride ion to form allylic carbocation. Here an allylic carbocation is formed. It is a primary carbocation. If methyl group shift from this first position to this carbocation or carbon atom, positively charged carbon atom, then a tertiary carbocation, a more stable tertiary carbocation will be formed, and hence methyl shift takes place because of the formation of a tertiary carbocation by this rearrangement. Tertiary carbocation, it is more stable than this allylic carbocation. Okay, and in the next step, a hydrogen is eliminated in presence of DDQ anion as proton to form a carbon-carbon double bond. Aromatization completed to form this molecule which is called 1,2-dimethyl naphthalene. This is the mechanism of this reaction. Okay, it is another example of aromatization reaction given by DDQ. If you treat 2,3-9-trimethyl 1,4-dihydroanthracene, 2,3-9-trimethyl 1,4-dihydroanthracene with DDQ, aromatization takes place to form 2,3-9-trimethyl anthracene. It is 2,3-9-trimethyl anthracene. You know the positions are, here it is first position, first carbon, second carbon, third carbon, fourth carbon, then fifth, sixth, seventh, eighth, ninth, 10th. These two are 9 and 10 position, and so this molecule is named as 2,3-9-trimethyl 1,4-dihydroanthracene, and so the product will be 2,3-9-trimethyl anthracene. Here this molecule 2,3-9-trimethyl 1,4-dihydroanthracene reacts with DDQ. Dehydrogenation takes place to form 2,3-9-trimethyl anthracene. It is an example of aromatization reaction given by DDQ. Okay, the mechanism of the reaction can be represented like this. Here DDQ first capture a hydrogen as hydride ion from this benzylic position. It is the benzylic CH2 group. From here a hydrogen atom is captured by DDQ as hydride ion to form benzylic carbocation. Benzylic carbocation, and this benzylic carbocation again, rearrangement takes place. There is the one of the pi bond shifted here to form a tertiary carbocation. Tertiary carbocation. It is primary carbocation. It is tertiary carbocation. So it is a stable carbocation which is formed by the shift of this pi bond to the carbocation position. So you will get this tertiary carbocation, and from this tertiary carbocation a hydrogen is eliminated as proton to form a carbon-carbon double bond here. So we will get this 2,3-9-trimethyl anthracene. Here aromatization completed by this process, and hence we get 2,3-9-trimethyl 1,4-dihydroanthracene as the product. Right? This example is also an aromatization reaction. Here 2,6-diethoxy, 2,5-dimethyl, 2,5-dihydropyrazine, which on reacting with the DDQ, aromatization of the ring takes place to form 2,5-diethoxy, 3,6-dimethyl pyrazine. It is 2,5-diethoxy, 3,6-dimethyl pyrazine. Here also DDQ first capture a hydrogen atom as hydride ion from this position, allylic position. Thereby a carbocation, a tertiary carbocation is first formed, and then a pi bond gets shifted to this position, from this carbon nitrogen position to carbon carbon position. Thereby nitrogen will get a positive charge. Then in the next step, DDQ anion capture a proton from this position, thereby a double bond is formed between carbon and nitrogen here. So you will get this product. Okay, it is all about aromatization reaction. You can see in all these aromatization reaction, DDQ dehydrogenate the reactant molecule to form an aromatic product. Dehydrogenation takes place in two steps. In the first step, hydrogen is captured by DDQ as hydride ion, and in the second step, hydrogen is captured or eliminated by DDQ as proton. Thereby a dehydrogenation takes place. Dehydrogenation reaction takes place. The overall reaction is aromatization. Okay, this much about the aromatization reaction. Okay, the next important application of DDQ is extension of conjugation. It is used to extend the conjugation. Thereby a more stable product will be obtained. For example, 1,2-diphenyl ethane. It is 1,2-diphenyl ethane. 1,2-diphenyl ethane. 1,2-diphenyl ethane on treated with the DDQ. Dehydrogenation in these two carbon atoms takes place. As in the previous case, first DDQ capture a hydrogen from this benzylic position as hydride ion to form a benzylic carbocation. Benzylic carbocation. And in the next step, DDQ anion capture a hydrogen atom as proton from this benzylic position to form a carbon-carbon double bond. Thereby extended conjugation takes place. Extension of conjugation takes place, whereby forming trans-stilbene. Here trans-stilbene is formed by the formation of a carbon-carbon double bond between these CH2 groups. Here hydrogen is first captured by DDQ as hydride ion to form the benzylic carbocation, and in the next step DDQ anion formed, then capture a hydrogen atom as proton from here to form a carbon-carbon double bond. Thereby this system becomes conjugated system or forming trans-stilbene. Trans-stilbene. It is a conjugated system, and so we can say DDQ is used for the extension of conjugation in a molecule. Okay, DDQ is used to form alpha-beta unsaturated carbonyl compound. Alpha-beta unsaturated carbonyl compound. For example, when a cyclic ketone is treated with the DDQ, it forms alpha-beta unsaturated ketone. For example, this cyclic ketone on treating with the DDQ, two products will be obtained. One is this enol, an alpha-beta unsaturated ketone, and other is this alpha-beta unsaturated ketone. You know, this product, this second product, is the major product. By understanding the mechanism involved in this reaction, the formation of major product can be explained. For example, when this ketone, cyclic ketone, reacts with the DDQ, see, first of all, this keto form gets enolized or an enol form is produced. It is the enol form. Here hydrogen atom from this carbon atom shifted to this oxygen atom, thereby a double bond is formed here, or keto-enol tautomerism takes place, and hence this enol is obtained. And here is an allylic position from where DDQ capture hydrogen atom as hydride ion to form an allylic carbocation. Allylic carbocation. After the formation of this allylic carbocation. This enol gets tautomerized to ketone again. There it is, the ketone. Then in the next step, DDQ capture the hydrogen atom from this carbocation as proton. Thereby a carbon-carbon double bond is formed here to form this product. You can see this carbocation is a primary carbocation. If the mechanism is like this, for example, enolization takes place like this. Instead of enolization or hydrogen shift from this carbon atom, takes place to form this enol. DDQ capture a hydrogen atom from the allylic position of this carbon-carbon double bond, that is this CH group, where hydrogen atom is captured by DDQ as hydride ion to form a tertiary carbocation. Here tertiary carbocation formed instead of primary carbocation here. And so a tertiary carbocation, which is more stable carbocation, is formed here. Then as in the previous case, again ketone is formed by the tautomerization, and in the next step a proton is eliminated in presence of DDQ anion, thereby forming this enol. Okay, and this enol also has an allylic position here. DDQ again capture the hydrogen atom from this allylic position as hydride ion to form an allylic carbocation. Again, this allylic carbocation eliminates a hydrogen atom as proton, which is captured by DDQ anion. Thereby a double bond is formed, and hence molecule with the extended conjugation is formed here. So this product is more stable. Because of the extended conjugation and also the mechanism involved a tertiary carbocation instead of primary carbocation, and hence it is the major product here. Okay, and so we can say DDQ is used to form alpha beta unsaturated carbonyl compound. It is very important, especially in the natural products chemistry. Okay. Another very important application of DDQ is its oxidation of allylic or benzylic alcohol. Oxidation of allylic or benzylic alcohol by means of DDQ. For example, here this alcohol, on treating with the DDQ in presence of dioxide solvent, we get this ketone. Here allylic alcohol gets oxidized. It is an allylic alcohol. This gets oxidized to ketone or enol, alpha beta unsaturated ketone. So here allylic alcohol gets oxidized in presence of DDQ. If you examine the mechanism of this reaction, DDQ first of all absorb a hydrogen atom from allylic position. Here it is allylic position, this position also allylic position. But if hydrogen is captured as hydride ion from this position, a more stable tertiary carbocation is formed. But if hydrogen is eliminated from here as hydride ion, a primary carbocation is formed, and hence preferentially this hydrogen is eliminated as hydride ion, and then say tertiary carbocation is first formed like this. Then in the second step, DDQ capture a hydrogen atom as proton to form the required product, that is enol, alpha beta unsaturated product, that is this product. That is the mechanism of allylic oxidation using DDQ. Okay. Similar mechanism as we discussed is also applicable here also. See, it is an allylic alcohol. It gets oxidized to a ketone. That is one alpha beta unsaturated ketone. The same type of mechanism takes place here also. DDQ first capture a hydrogen atom from this position as hydride ion to form a carbocation, a tertiary carbocation. Then in the next step, a hydrogen is eliminated from this OH group as proton, thereby forming this alpha beta unsaturated ketone. Similar mechanism as we discussed. Similar mechanism. Here also DDQ capture a hydrogen atom from this position, that is the benzylic position, benzylic hydrogen. Here a hydrogen is present, that is benzylic hydrogen, which is captured by DDQ as hydride ion to form benzylic carbocation. Then DDQ capture a proton from this OH group, thereby this enone is formed as we discussed in the previous case. Okay, so we will get to this alpha beta unsaturated ketone. This ketone is formed. Okay, that is also important. See this example. Here DDQ first capture a hydrogen atom as hydride ion from this benzylic position, thereby a tertiary carbocation is first formed here, and in the next step DDQ capture a hydrogen atom as proton from this acid group, thereby forming this heterocyclic compound. It is isobenzyl furanone, a substituted isobenzyl furanone. It is a heterocyclic compound. Here actually oxidative cyclization reaction takes place. Oxidative cyclization reaction takes place. Hydrogen or dehydrogenation or oxidative cyclization takes place. Here dehydrogenation followed by cyclization takes place, and hence this reaction is called oxidative cyclization. And so DDQ can be used for oxidative cyclization process. Here it is an example. Okay, the mechanism can be represented here. See, first as I have discussed, first I capture a hydrogen atom as hydride ion by the DDQ to form a benzylic carbocation. Then DDQ capture the hydrogen atom from this carboxylic acid group as proton, then thereby forming this ion, diion, that is negatively charged and positively charged ions are here, thereby ring closure takes place by bonding these two ions, thereby forming these products. That is the mechanism involved in the oxidative cyclization of this compound to form this product. Okay, that is one of the important application of DDQ, that is oxidative cyclization reaction. Right. Another important oxidative cyclization process is taking place in this case also. See, for example, DDQ first capture a hydrogen atom from this benzylic position as hydride ion to form a tertiary carbocation. To this tertiary carbocation, this pi bond gets shifted, thereby cyclization takes place, a 5-membered ring is formed, and from this position, this becomes CH2 group, and from this position a hydrogen atom is captured by DDQ as proton, thereby a double bond is formed, a new double bond is formed here. So we will get this product. Actually, an oxidative cyclization reaction, as in the previous case, takes place. Okay. Another important example of oxidative cyclization reaction is represented here. First of all, DDQ capture a hydrogen atom from this benzenic position as hydride ion. Thereby, a benzenic carbocation is first formed. And so, when this double bond shifted from this position to this position, here there will be a carbocation form which would be tertiary carbocation. The first formed carbocation is primary carbocation. You know, tertiary carbocation is more stable than primary carbocation, and hence this double bond or the pi bond gets shifted from this position to this position in order to form a tertiary carbocation here. That is the first step. And in the second step, DDQ capture a hydrogen atom as proton from this position to form oxygen negatively charged ion. Here a carbocation position, here is a positively charged carbocation, here is a negatively charged oxygen atom. Then these two form a new bond here, and hence a six-membered ring is formed here, or oxidative cyclization takes place to form this product. Okay, the mechanism of this reaction is represented here. As I was discussed, first DDQ capture a hydrogen atom as hydride ion from this position, that is benzenic carbon position. Thereby a carbocation is formed, but it is primary carbocation. By shifting this pi bond from here to here, thereby a tertiary carbocation is formed. It is more stable than primary carbocation. And in the next step, DDQ capture a hydrogen atom as proton from here to form or this, in another way, this lone pair of electron make bond with this positively charged carbocation to form this ion, positively charged ion. From this, hydrogen may be captured by DDQ as proton, thereby a neutral molecule, a six-membered heterocyclic compound as represented here is formed. It is another important example of oxidative cyclization reaction. Okay. So we had already discussed almost all the types of applications of DDQ, such as aromatization reactions given by DDQ. That is, we can convert a cyclic unsaturated compound or cyclic enes to aromatic compound or aromatization reactions. Then we can use DDQ for stabilizing a molecule by extending the conjugation in the molecule using DDQ. Using DDQ, we can, or DDQ can be used for the oxidation of allylic and benzenic alcohols. It is also used for the formation of alpha-beta unsaturated ketone. And in certain cases, it is used for intramolecular cyclization also. All these have been discussed with very important examples. I think you might have got a clear idea about these applications, and with this I conclude this video. Thank you for listening. Thank you.